So thank you, no disclosures again, and thanks to ICS for a very generous travel award. So irrespective of any material being implanted in the body, there is going to be a foreign body response. And more and more literature have come out where a lot of these mesh complications are associated with the undesirable foreign body response. So one of the key things here is, again, we want more of M2 type of macrophages which have an anti-inflammatory and healing effect rather than the M1 macrophages. So the aim of this study is how can we make meshes better. So from the sheep study, we still understood that using a non-degradable mesh gave us a lot of exposures early on, and so we still wanted to make it better. And it's a long process, a difficult learning. Surgeries are complicated. So the next approach that we took was using a degradable polymer and then combining it with the power of endometrial stem cells, so that we use a better, more friendly polymer and use fabrication techniques such as nanotechnology methods to improve the meshes. So one thing about the endometrial stem cells is they are very powerful in terms of their regenerative capacity, because every month after menstruation, the uterus is healed to its perfection, and so we want to use this power of endometrial stem cells to help heal in the vagina as well. So we use a technique called electrospinning, where we use a polymer which is a copolymer of PLA and PCl, combining it with gelatin. So the reason why nanofabrication is extremely attractive, because it gives a high surface area compared to the volume, and the cells interact much better, which you can see they produce this nanoscale philopodias to interact with the material. So we hope that this will lead to a better foreign body response, more desirable one. So we fabricated two meshes. Mesh 1 was without gelatin. The mesh 2 was with gelatin. And we saw there's a significant difference in fiber thickness and pore size. We did not find much difference in the mechanical properties of these meshes, except that adding gelatin made it hydrophilic. And because it was hydrophilic when we added gelatin, so what you see is on one, there is a cell that is on top of the mesh, whereas when we add gelatin, it actually enables the cells to go inside and it gets trapped. So we hope that this will actually keep the cells longer after we transplant them. So there's more cell-cell and cell material interaction. So when we implanted them in mice, we saw that because of this trapping effect, the cells were kept much longer, up to 6 weeks at the site, and there was a lot more infiltration of cells, which was what we desired. And so I'll just skim through these, where MSCs actually protected rapid degradation of the mesh, and also increased formation of collagen, which we sort of evidenced through many different experiments. And we also saw that eMSCs actually increased M2 macrophages, and we did a 96 gene expression analysis, and still analyzing that amount of data. But essentially what we found is in mesh number 1, MSCs increased genes related to ECM and reduced inflammation-related genes. And in the mesh number 2, which was already quite good in the earlier results, we found that they increased genes related to protective immune response. So in conclusion, we think electrospinning is a really good technique to produce mesh. It looks like a tissue paper, so one would think that it is not, it's very fragile, it would tear when we suture it, but it actually doesn't tear, it stays. And they also gave us these really important aspects of the cell-tissue interaction, which is growth, retention of the cells, M2 macrophages, and making new collagen. So we think this is quite a good material and quite promising going into the future. So our next step would be to use the sheep model to study these meshes. Yeah. Thanks, everyone. It's a big team. And also, Hope to see you in Melbourne, ICS 21.
Thank you, and for a really nice talk. And I think it's very good that you also looked at porosity, which makes, which really led to the improvement of the polypropylene devices. And one of the strengths of the PVDF mesh, as comparison to the polypropylene, is that it keeps its porosity also under strength.
Yeah.
So, have you compared your porosity size and also under stress with your new tissue? Is this, do you gain the same porosity?
So if you compare these meshes to the polypropylene or other
PVDF,
the pore sizes are extremely small. So, but however, the material is completely different, and because the surface area is so high, the way the polypropylene works, this one doesn't work that way. The cell material interaction is completely different.
So we would have to define new criteria how to make. You think the increase in surface, then it doesn't matter that the pores are different?
Yes, I think because the material and the fabrication techniques are so different, we cannot compare that the porosity of the polypropylene meshes and these. So we have to experimentally determine a new scale of what if 2 or 3 of polypropylene, what an equivalent of the degradable mesh would be, because they work so differently. It's like comparing apples and oranges, I feel.
Thank you.
I was just wondering, in your first study, why do you think you had this immense difference in erosion rate? Because perhaps that could help surgeons if you could find a reason.
That's a very good question. So when it's, I feel you use same ingredients to make cookies and bread. One is very stiff, other is soft. And I think it's the same kind of thing when we use method 1. The product that we get is not as drapable, whereas in method 2, it's quite drapable and the cells go on. So the stiffness overall is much higher in method 1, which we suspect is one of the reasons why we got this high exposure. And once we suture the mesh in and then it sort of contracts, it doesn't sort of go well. And we had that, like our rate was so high, actually more than the published rates, really. So we feel that stiffness and overall how the product is made a big difference. So.
Okay, thank you very much.
Thank you so much.
Presentation.